we want to introduce cylindrical coordinates. Now, cylindrical coordinates are essentially the same as polar coordinates, but in 3 dimensions. We leave x as r cos theta and y as r sine theta in the xy plane, and then z remains as z. So it means we probably have a circular base in the xy plane or an integrand involving x squared plus y squared in some capacity. So if I have a triple integral of the form f of x, y, z dv, then when we switch it to cylindrical, it becomes a triple integral. Of course, we change our limits to suit the r, the theta, and the z. I have f of r, theta, and z, but then like before, I introduce r to go with dz, dr, d theta. Now let's consider the following situation. I have a downwards opening circular paraboloid, and it intersects with the xy plane, and I would like to find the volume bounded by this shape. Now, the intersection with the xy plane is where z equals 0, so this circle would be x squared plus y squared equals 36. So if I was to write this using rectangular coordinates, then the x would go from -6 to 6, y would go from the bottom to the top half of the circle, so it would be the negative square root of 36 minus x squared to the positive square root of 36 minus x squared. And then the z would go from, in this case, 0 to 36 minus x squared minus y squared. Now, this, if I integrate it, will just simply be 1 dv. So what we want to do is integrate this using cylindrical coordinates. Even though we know how to do it using rectangular, this part here would be very, very difficult to work with. Now, if I translate this into cylindrical coordinates, we see that we have the circle on the xy plane, so 0 to 2 pi for theta, 0 to 6 for r, and now our z limits become 0 to 36 minus r squared because we are replacing x squared plus y squared with r squared, and then the addition of this term right here. So the integration should be relatively simple at this point. So we have rz evaluated from 0 to 36 minus r squared, dr d theta. So then r basically times this would be 36r minus r cubed, dr d theta, which would give us then 18r squared minus 1/4 r to the 4th from 0 to 6 d theta. That quantity right there would be 0 to 2 pi of 324 d theta. And since we have a constant integrand, we can just multiply by the 2 pi, and we get 648 pi. So that would be the volume of the shape. We've computed this before, but now we're doing it as a triple integral. So now suppose I had inserted a density into here as well. Well, the process would still be the same. Now, if you check the notes on Canvas, I've done a very long, lengthy problem to go much further to give you much more experience and practice with this.